New cloud-based applications and services are creating new requirements for network performance, including ultra-reliability and low latency. At the same time, networks are becoming more complex. Many now feature distributed clouds, multiple domains, and multiple technologies. In this video, we focus on how the multi-layered nature of networks can impact service availability. Let's zoom in on the transport network between a core data center and an edge cloud. This transport network is made up of several routers, with logical connections between them. The network is managed by a central controller, such as the Nokia Network Services Platform, or NSP. We want to create an ultra-reliable service from the core data center to the edge cloud, which requires IP connectivity between the two gateways. So we use NSP to automatically create a path that complies with the SLA requirements. We also create a backup path to ensure the service stays up and running if there is an issue on the main path. If we cut the link on the main path, traffic should be switched to the backup path to maintain the service. However, despite this protection, the service is interrupted. Something has gone wrong, even though we created a backup IP path. But what's causing the problem? To find out, we need to see the physical connections in the layer underneath, so let's view this network architecture in 3D. The IP traffic is running over an optical infrastructure. As the team operating the IP network, we currently have no visibility of this optical infrastructure. If we had visibility, we would see a complex architecture with several optical devices connected to each other with optical fibers or conducts. We would then realize that our main IP path and backup IP path are not taking diverse routes. They are sharing the same optical link in one section. We want to avoid this scenario. If this link is broken, the two IP paths will be impacted, and the service will be interrupted. We can prevent this from happening using information on shared risk link groups, or SRLGs. This information is available from an optical management system such as Nokia WaveSuite. An SRLG is a grouping of all the links that share a common fiber or conduct. The IP controller can retrieve SLRG information from the optical management system. The IP operations team can then use the information to recalculate the IP paths so that they use other viable optical links. This allows for truly diverse IP paths. Ensuring true path diversity requires coordination between the IP and optical management systems. Nokia NSP and Nokia WaveSuite have this IP-optical coordination capability, which enables many other use cases. We can group these use cases into three broad categories: discovery, correlation, and optimization. Discovery allows us to accurately inventory the discovered network topology, the cross-layer interconnections, and the existing services. One example of a diversity use case is path diversity analysis, as illustrated in this video. Correlation across layers allows us to identify root causes and minimize the impacts of maintenance operations. Optimization use cases ensure efficient and effective network engineering operations by enabling cost-effective port redundancy and automated cross-domain connection management. IP-optical coordination is becoming more critical as the optical and IP layers become more integrated through the use of pluggable colored optics such as 400ZR and 400ZR+, which can be deployed in routers. These pluggable optics enable operators to connect routers directly over coherent wavelengths, but they blur the line between IP and optical domains, which creates a set of operational challenges that must be addressed. Coordination between IP and optical domains through the Transport API, or TAPI, will be essential for enabling efficient end-to-end planning, provisioning, and troubleshooting. The results of effective IP-optical coordination are increased network utilization, improved network resiliency, and accelerated service instantiation.